Have you ever wondered how scientists organized all the elements we study today? Before the discovery of protons, neutrons, and electrons, scientists attempted to classify elements by arranging them in order of atomic weight, which we now call relative atomic mass. In 1829, Johann Döbereiner noticed that some elements could be grouped in threes. He called these groups triads. The elements in each triad had similar chemical properties, and the mass of the middle element was approximately the average of the other two. This was one of the first attempts to systematically organize the elements. Later, in 1864, John Newlands arranged the known elements in order of increasing atomic mass. He observed that every eighth element had similar properties. He called this pattern the law of octaves, comparing it to the repeating pattern of musical notes. However, his idea was not accepted at the time because it did not work for all the known elements. Then, in 1869, Dmitri Mendeleev developed a more successful periodic table. He arranged the elements by increasing atomic mass, but he also carefully considered their chemical properties. Importantly, he left gaps for elements that had not yet been discovered and placed elements with similar chemical properties in the same groups. Mendeleev even predicted the properties of the missing elements by studying the properties of the elements around each gap. For example, he predicted an element he called AQA silicon, which he believed would fit into a gap below silicon. Later, germanium was discovered, and its properties closely matched Mendeleev's predictions. This provided strong evidence that his periodic table was correct. However, there were still some problems. When elements were arranged strictly by atomic mass, some pairs appeared to be in the wrong order. For example, iodine and tellurium did not seem to fit correctly based on atomic mass alone. Iodine has a slightly lower relative atomic mass than tellurium. Therefore, based purely on atomic mass, iodine should be placed before tellurium. However, iodine has chemical properties similar to chlorine and bromine. To ensure iodine lined up with chlorine and bromine in the same group, Mendeleev swapped the positions of iodine and tellurium in his table. Mendeleev did not know about isotopes. The later discovery of isotopes explains this apparent reversal. The positions of iodine and tellurium were reversed because iodine has one naturally occurring isotope, iodine-127. The most abundant isotopes of tellurium are tellurium-128 and tellurium-130. The high relative abundance of these heavier tellurium isotopes gives tellurium a greater relative atomic mass overall. This explains why atomic mass was not always reliable for ordering elements. However, the atomic number of tellurium is 52, and the atomic number of iodine is 53. This means they are in the correct order when arranged by atomic number in the modern periodic table. In 1913, Henry Moseley discovered that elements should be arranged by atomic number, the number of protons, rather than atomic mass. This solved the inconsistencies and led to the development of the modern periodic table. In the modern periodic table, elements are arranged in rows called periods in order of increasing atomic number. Elements with similar chemical properties are placed in vertical columns called groups. The table is called the periodic table because elements with similar properties occur at regular intervals. This happens because elements in the same group have the same number of electrons in their outer shell. And that is how the periodic table developed into the powerful tool we use in chemistry